Okay, in this presentation we are going to investigate the proportion of electric car ownership in two populations. So this parallels the type of thing that you would come across in an undergraduate statistics course, and in fact we're going to use that a lot. So we're going to use that sort of approach there, looking at confidence intervals, standard errors, test statistics, and so on. We won't be using prop.test in this particular instance. It's just to actually learn about approaching things a different way. So this exercise involves simulating data, estimating confidence intervals from first principles, and performing hypothesis testing from first principles to investigate the proportion of electric cars amongst registered cars in two large populations A and B. This exercise demonstrates how to simulate data, estimate confidence intervals, and perform hypothesis testing. Okay, so this is what we're asked to do. A researcher wants to investigate the proportion of electric cars amongst all registered cars in two large populations denoted A and B. Two samples are considered, one from each population. The first sample consists of NA equals 900 registered cars, while the second sample consists of NB equals 1,200 registered cars. The type of each car, electric or not, is assumed to be independent of the type of other cars in the sample. Okay, so this approach will requires to simulate some data. Simulate the two samples in R, assuming that the proportion of electric cars in population A is 0.02, while in population B it is 0.025, and save the simulated samples for later use. So you must use the command set.seed12345 to initialize the random number generator before you start the simulation. Okay, the true proportion of electric cars in the two populations are unknown to the researcher. They're known to us, but not to the researcher. Well, we're setting up a sample anyway, so maybe it's not even known to us. The researcher wants to estimate them. Determine an equal-tailed 99% confidence interval for the difference in the true proportion of electric cars in the two populations using your sample data. And finally, based on previous knowledge, the researcher believes that the proportion of electric cars in population A is lower than the proportion of electric cars in population B. Okay, perform a hypothesis test to investigate this belief using your sample data. In doing so, you should include the following steps in addition to other necessary steps. So this is where we're told to specify the approach where we're using the test statistic, the standard error, etc., etc. Essentially, the pen and paper approach, as I call it. So, compute the value of a suitable test statistic under an appropriate normal approximation. Okay, so that is the point estimate divided by the standard error. Compute the p-value of the test, and then state your conclusion on the calculated p-value. Okay. So, simulating the two samples, we initialize the random number generator with the seed 12345. Okay. Now, the intended outcome of this is a sequence of 900 zeros or ones, where 0.02% should be ones in the case of population A and 0.025 in the case of population B. Bernoulli trials, etc., is what we're getting at there. Binary outcomes. Okay. So the probability of a 1 is 0.020 for population A and 0.025 for population B. So essentially the number of trials is 1, so it's the number of successes and the probability of success. Bernoulli trials is what I'm getting at anyway. Or binom, that is how we create random numbers according to the binomial distribution. So we just set them up there like that. Data.A and data.B are binom 900 and 1200, and then we have the details I just went into previously. Okay, so have a quick look at it there. That's the first 150 outcomes on both cases. I just picked a lot there because there isn't really a whole lot to look at. It's just lots of zeros, but you do start to see the odd number 1 scattered in there. Okay, so anyway, determine a 99% confidence interval for the difference in proportions. Okay, so this is where we are using a lot of the skills we might have built up in pen and paper exercises, so to speak. So using the sample data, determine an equal-tailed 99% confidence interval for the difference in true proportions of electric cars in populations A and B. So we have the sample sizes there, 900 and 1000 respectively, but let's get them there again. NA and NB. So essentially so this fits with the type of formula that you should probably be familiar with. And what we're going to do there is estimate the proportions of both. So P hat for A is the sum of A divided by the length of A, and P hat of B is the sum of data.B divided by the length of the data.B, NB. Okay, so that gives us our sample estimates, our P hats for A and B, our sample proportions. Our point estimate is essentially the difference between these two numbers here. Okay, so it is, in the first case, it's approximately 2.1%. In the second case, it is approximately 2.9%. Okay, so there is a difference, but is it significant? So what we're going to do now is calculate the standard error. Okay, now just if you recall, there is a standard error formula that you would use for confidence intervals of difference of proportions, and there is a different one you would use in the context of hypothesis testing. So what we have here is P hat of A times 1 minus P hat of A divided by NA plus P hat of B times 1 minus P hat of B divided by NB. And then we get the square root of that. Okay, so essentially that's the standard error formula just coded out. It's a little bit long-winded to look at, but it's straightforward enough there. And you probably should be familiar with P times 1 minus P divided by N and getting the square root of that. So the next bit is the quantile. So you probably will be familiar with 2.576 if you've done this as part of an undergraduate statistics course. It's like 1.96. It's one of these numbers that crops up a lot. So this is how we will sort of get it programmatically. We're going to save it as a little vector called ZS, or Zs essentially. We have C minus 1 and 1. That's essentially just to control the sign, have a minus and a plus, essentially implement a plus or minus. And Q norm of 0.995. So essentially what we want is an even-tailed interval comprising 99% of the distribution. Okay, so it's the 0.5% up to 99.5%. It's between those two values. So there we get it there, minus 2.576 to 2.576. Okay, so essentially what we're going to do now is piece this all together. And the general structure of a confidence interval is the point estimate. Here is the difference between the two P hats, P hat A minus P hat B, plus ZS times the standard error ESE.df. Okay, so when we piece it all together, point estimate plus or minus quantile times standard error. Okay, so we save that as confidence interval of P difference ci.p.diff, which is our confidence interval. So there we have the numbers there, minus 0.0256 to 0.0095, just ignoring a couple of the decimal places. So the 99% confidence interval is minus 0.0256 to 0.009. Okay. And finally, what we're going to do now is calculate all the necessary values so we can perform a hypothesis test. So here we are testing whether the proportion of electric cars in population A is lower than population B. Okay, so you state the hypotheses as always. You probably can even put a little sentence in there if you want. PA is equal to PB, which is to say no difference, and PA is less than PB, which is to say the proportion of population A is lower. So, same approach, although just accounting for the fact that the standard error formula is different in this case. So here we use the aggregate proportion, the total number of registered cars, electric cars out of the total number of all registered cars, sum of data.A plus sum of data.B divided by NA plus NB. Okay, so P hat common essentially gives the proportion of all cars, all electric cars over the two populations. The standard error is based on that. So here we have the standard error ese.diff.h0 on the expected sampling distribution under the null hypothesis, or the standard error. And we have square root of p hat common times 1 minus p hat common times 1 over na plus 1 over nb. And again, a little bit long-winded, but essentially this is just a codification of the usual standard error formula that you would encounter at some stage. So the test statistic, let's go back here, that is our point estimate divided by our standard error. So that here we get the stat.diff, that is our test statistic, and we get a value of minus 1.154. Okay. So let's get the p-value for that, and that is p-norm of stat.diff. Okay, so our p-value is 0.1242. So the value of the test statistic is minus 1.154, and the p-value is 0.1242. Since the p-value is greater than the typical significance level, so it's a one-tailed test, so we're comparing it to 5%, in this case 0.05, we do not reject the null hypothesis. We do not have enough evidence to conclude that the proportion of electric cars in population A is lower than in population B. So I think we'll leave it there. Yeah, we're all done.